Hello everyone, I'm Shunfan Zhou from Fudan University. I'm the lead author of this paper, Ferry State-Aware Symbolic Execution for Exploring State-Dependent Program Passes. This work is a cooperation with Zhemin Yang, Dan Qiao, my tutor Peng Liu and Ming Yang, and also Zhou, Wang, and Chenggang Wu. Currently, the popular dynamic program analysis and testing techniques include symbolic execution and fuzzing. And symbolic execution marks some input as symbolic and exclusive explore the possible passes in a program based on the propagation of symbolic input. For fuzzing, it focuses on the covering new blocks, and it will mutate the input and retrieve the feedbacks like block coverage and determine which input parts to mutate to cover more code. The common limitation here is that they both focus on low-level features like path or block coverage, but ignore the understanding of high-level program logic. Unfortunately, real-world programs need to process complex data. We take the format of a PNG image as an example. Such data is self-describing, and they are consisted of metadata and payload. And the metadata can have some implicitly constraints on the following payload. For example, the magic bytes in the header here indicates that this is a PNG image, and the size and the identifier fields describe the following content data. To handle such complex input, the programs usually implement non-trivial finite state machine. And this leads to the conflict. The machines of finite states can have infinite execution paths, and the execution and the existing techniques can be struggled by these paths and fail to efficiently exploit all these states. We take a real-world code snipped from the MP4 parsing as our motivating example. An MP4 file is conceptually consisted of several data boxes. To trigger this vulnerability, we need an MP4 file of 2 boxes. So here, the first box of type TRAK will take the branch in line 20 and set the value of variable saved size here. And we call this a variable the state describing variable in this paper. And the vulnerability can only be triggered in the state that saved size is positive. Then the second box of type TX3G is then used to trigger the real vulnerability. Since save size is positive, the line 13 will be taken. And this means the vulnerable size will also be positive. So there can be an integer overflow in line 16 here, and given the large box size. And this means the size of the buffer and the real size of the payload mismatch, leading to the real buffer overflow. Now let's see how the symbolic execution will handle this. There are 86 cases in the switch statement, which even more nested conditional statements, so it can suffer immediate path explosion during the exploration. While for the fuzzing, the storage is a little different, and the fuzzer will find that the save size variable is not tainted by input in most of the cases because it has a default value of -1. So the fuzzer will not deliberately mutate this input and try to mutate the value of save size, thus cannot trigger the vulnerability. Let's jump out of the existing works and see this example from the FSM level. Actually, there are a very limited number of states in this program, and only 4 different combinations of the variable box type and save size are enough to cover all the unique paths in this snippet. And this leads to our first insight, that the knowledge of program states can help improve analysis efficiency. But to really do that, actually, there can be 2 challenges to understand the program state. So the first is about how to recognize the state describing variables among all these variables. Because you can see that the state describing variable can have no semantic features and no structural features compared with normal variables. And the second challenge here is that how to determine the runtime program states, because we need to learn about the division of different value ranges. So we can determine that given the current value ranges of these state describing variables, whether this is an exploration path of an explored state. So to tackle these challenges, we first conduct an investigation on the programs with state machines to understand their characteristics. So we can conclude the characteristics as follows. So first, they all receive a sequence of input from a single input source. And in most cases, this is a file. And also in the programs, they will handle the inputs sequentially. And normally there can be a input handling loop here. And we call that the input part, which has been processed in the current iteration, we call it the current input. And the input part, which has been processed in the previous iteration, we call them the earlier inputs. So when processing the self-describing data, the most important characteristic is that we find that the programs, they maintain the program state with one or more state describing variables. And this means that the earlier inputs, they can affect the value of state describing variables. And we say that they can affect the state of programs. And further, these states will used to determine the process of the current input, in that such variables may have the ability to affect the control flow by maybe affect the branch taken of certain conditional statement. Okay, so to tackle this problem, we proposed the world's first program state-aware symbolic execution engine called Ferry. And it will continuously recognize the state describing variables and the current program state during the analysis, and kill those exploration passes of explored state. We further propose optimizations to tackle the complexity of real-world programs. Also, we rely on the necessary condition we conclude from the previous investigation to recognize the state describing variables. So there can be two necessary conditions here. So the first, the variable must be affected by input in some execution passes. So this means the variables can be tainted by the input with both explicit and implicit data flow. And second, the variables must be able to affect some branch taken, so it has the ability to affect the control flow of the future input process. Correspondingly, we use taint analysis to determine whether the variables are affected by input. And we introduce actual instrumentation during symbolic execution to determine whether these variables can affect control flow. And it is worth noting that this process happens in a cross-path way. So which means variables can be input determined in one path and branch related in another. And we will still consider it state describing. For example, safe size is tainted by input in the blue path here, while it is checked in the conditional statement in the orange path, but Ferry will still label it as state describing after both paths are explored. To recognize the runtime state of the programs, our second insight here is that the state transitions happens when the path constraints change. So the runtime state is described by the path constraints on all the state describing variables. For example, the two values of box type are determined by the two cases here, and the safe size is also similar. So we can catch the state changes by monitor the constraints on the state describing variables. Here, so normally in the programs, the state transition points there can be three kinds of state transition points. So the first is when the variables are initialized. And the second is when the data constraints are changed. For example, the variable can be assigned a new value, or some branch taken changed the path constraints. And the third is that when some variables is deleted. So with the analysis above, Ferry can automatically construct the finished state machine like this. Please refer to our paper for the full construction process, because I skipped this for the limitation of time. Also, we find that the real-world programs do not handle all the input sequence in one functions. Instead, the input is divided into different parts and handled by the different functions. For example, in our motivation example, the payload is reserved for future process in line 18. And so to avoid state explosion, we automatically recognize the boundary in the input and provide partially concrete input from seed files. So please refer to our paper for more detailed optimizations. Okay, finally, we conduct experiments to evaluate the efficiency of Ferry. And we use the benchmark of both Google FuzzBench, which consists of 20 programs at that time. And we further collect some real-world programs with state machines. And finally, we get 13 programs, which include the image, video, and audio, and the PDF and the binary processing. And we compare our tool with the existing symbolic executors, including Anger and Klee, and also the state-of-the-art fuzzers like AFL, Angora, and QSIM. And our evaluation mainly focuses on two parts. So the first is more traditional, for example, what about the code coverage of our tool compared with others? And the second, since we focus on the program state, we further evaluate the state coverage of our tool compared with others. So in short, compared with existing symbolic execution tools, Ferry achieved about 40 more basic blocks coverage and about 45% more branches. And compared with existing fuzzing tools, given the same seeds, Ferry is able to cover more basic blocks and branches. And during our evaluation, we successfully find 3 zero-day vulnerabilities. We have followed the responsible disclosure, and all these vulnerabilities has been fixed before the publication of this paper. Further, to evaluate the state coverage, we manually filter the state-related vulnerabilities in CVE database and see whether all these tools can reproduce these vulnerabilities. Our results shows that Ferry can find twice as many cases compared to other symbolic executors, and given the same seed files, only Ferry with shortcut symbolic execution is able to locate all these vulnerabilities. Finally, we construct a state-related benchmark called River, which contains 6 real-world programs and 110 state-dependent vulnerabilities. And compare with Ferry, which is able to locate all these vulnerabilities, other tools can only locate as many as 50% of them with shallow depths. And our evaluations shows that Ferry is able to cover more in-depth code locations compared with existing tools. Thank you.